So I was going to make this a warm up, but let's just talk through it. So here's what I've got. I think we're all cool with order of a differential equation, right? We know that the order of a differential equation is just the highest derivative in that equation. So if you have like a third derivative, it's a third order. I started to write down this, but I kind of realized it wasn't true. But let's see. So I've got a differential equation is linear, dependent variable, typically y, although there's certainly a problem. I think problem 5 in your homework assignment has u as the function or the dependent variable. I wrote only appears raised to the first power, but then I thought about it more and did some Googling, and here's really more of an accurate way of saying it. If your dependent variable y and its derivatives can be written as being raised to the first power and multiplied by functions of the independent variable x. So here's what I want to point out, and we'll just let me. Sorry, the lighting here. I just know this feels terrible to me. Let me turn off this clip. What I want to point out is that third equation, that third example is not linear. Because even though you have y to the first and y prime to the first, them being multiplied by each other is problematic. So to be linear, you really have to have each derivative of y only multiplied by maybe functions of x or constants, but not another y thing. So this definitely, this example here, this is first degree, but it is non-linear because of the 3y times y prime there. That makes it non-linear. These other two equations are both linear because each derivative and the function itself, so here y double prime, y prime, and y, they're all multiplied by things that aren't y's, right? They're multiplied by functions of x, which is totally fine. So this one here is certainly second degree, right? Because you've got a second derivative, and this is linear. This next one is third degree because we've got a third derivative, and also linear because each derivative is only multiplied by functions of x or constants. So I will also point out, just kind of to say one more thing about this, and again, you should ask questions if you got them. I would also point out that something like this one's in this, I hope this one's a little more obvious, but something like this, where you had, say, like, I don't know, y prime plus 1 over y times x squared equal to 5. This one is also certainly non-linear, because even though it looks like you have a quote unquote y to the first, that's 1 over y is really a y to the negative first. So this is also certainly non-linear. And it would be a first degree. And I believe, although I'm not 100% sure because I really am not up on what it means to be homogeneous, I believe, oh, well, you said homogeneous, but only in the context of standards. So this one can't be written in standard way, so I don't know what to say about it. I believe each of these first, I don't know. I really don't know about homogeneity. So we will only worry about it in the context of first order linear differential equations. Well, because really what I have here is a y prime plus y to the negative 1 times x squared. And so having y to an atypical power makes it nonlinear, or having y multiplied by something that's not just a function of x makes it nonlinear. So this is nonlinear in the same sort of way. This one here, then both right, a y double prime plus 5y prime plus 6xy squared equal to 0. This is also nonlinear, not because any of the multiples are issues, but because of the y squared. So that y squared is making it nonlinear. This y to the negative first is making it nonlinear. Y to the first, but specifically y to the first in the numerator, right? That's why I was trying to kind of trick you here. because technically you have a y to the first right there, but it's in the denominator, so it's really y to the negative first. So I guess if we wanted to write out words, we could say to be linear, you have to have each y and each derivative of y raised to the first power. So we can write this, although I don't think we really need to, but to be linear, we need y and all derivatives only to the first power, and coefficients to not be anything with y's in them. That's very, very general, I think. And I did some Googling, and they were the Google thing I found was like your differential equation should be written like this, where you have like some function of x times y plus some other function of x times y prime plus some other function of x times y double prime up until some, whatever derivative you're going to, say to the, I should make this a +1, some function of x times the nth derivative of y. This way of writing it is linear in y, because each y thing is only raised to the first power, and all the coefficients are not other y things. They're functions of your independent variable x, which is totally fine. Your x things don't have to be linear at all, right? You could have right? This could be, this could be e to the 2x. This could be sine of x, right? It doesn't matter what the functions of x are. We're only talking about linearity and order in terms of what y is doing. Questions about any of what I've said so far? Okay. Let's look at a couple examples I came up with to kind of mimic's not the right word, to think about how we might do some of these homework problems. So let's look at this first one here. Yeah, sure. So let's move this cursor out of the way. It's terrible. Okay. Let's see. Sorry, I'm not really good here. Okay. So let's look at the following. We're going to let y double prime plus 9 y prime equals 0. And we want to find all values of the constant r such that y equal to k e to the rx satisfies the differential equation. This is kind of like a slightly fancier version of verifying something's differential equation, a solution to the differential equation. They're already telling us that y equal to k e to the rx is a solution, but we have to figure out what values of r actually make it work. So the idea is the same as what we were doing at the beginning of the quarter, which is we're going to take y and we're going to find all the derivatives we need to then substitute into the differential equation. Specifically, we're not actually going to plug in y here, right? Because there's nowhere for y to go. But we do need to find both y prime and y double prime. That's very blurry here. That's fine. But okay. So our y is equal to k e to the rx, which means our y prime is going to be the derivative of that. So the derivative e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of that, y double prime, is going to be, again, the derivative k e to the stuff is going to be k e to the stuff times the derivative stuff again. So you're just going to multiply by another r. So you're going to get k e to the rx times r, or r squared. So those are my derivatives. And then I'm going to plug those into my differential equation to see if I can figure out what r has to be. So let's see. So I'm going to plug in y double prime. So I'm going to have k e to the rx times r squared plus 9 times y prime. So 9 times k e to the rx times r equal to 0. I'm just going to point out here, just because it's good to know this is right. This is my y double prime, and y prime. So now we're trying to solve this. Specifically, we want to solve for r. It should be the case that k can be anything, right? Like if they have a constant in there and they're not asking to solve for, that usually means it's kind of the kind of constant that can just end up being any value. And it is, it's true. So let's see here. I'm going to solve for this in the way I would usually solve an equation equal to 0 by factoring. So what can I factor out for both of these? A lot. A k, an e to the rx, and an r. So I'm going to factor out a k times e to the rx times r. What am I left with? Yeah, r plus 9. So technically here, there are two potential solutions for r. What's one of them? Yeah. All right, Caroline, what's the other one? You're like, I knew you were going to ask. It's okay. So here r can be -9, right? Because -9 plus 9 is 0. And what could r be here? If you want the whole thing to multiply to 0, it's all right. So here r could be 0, because 0 times all the stuff will give us 0. Now 0 is kind of a weird answer, which is why I'm not surprised it might have been a little hard to see. And in fact, generally that probably won't come up, but those are the two values that make ke to the rx a solution. Now, not that we're being asked to do this, but I do just want to point out that if r equals -9, the solution, which the problem isn't asking us for, is y equal to ke to the -9x. And if r equals 0, the solution is actually a little more boring. The solution is y equal to ke to the -0 times x. I didn't need a negative there, sorry. +0 times x, which is just y equals k. And it is a solution, it's just a not very exciting one, right? If y equals k, what's the derivative of a constant? So that's 0, that's 0, and 0 plus 0 is 0, so it works. So although it's kind of a boring solution, y equal to k is technically a valid solution to this differential equation, which means r equals 0 is a valid input for that constant. And then y equals ke to the -9x is also a valid solution. If we took the second derivative and took the first derivative and plugged those both in there, we would totally get a solution, or see that it's a solution, I suppose. Questions about any of this? I have a question. What order is my differential equation? Show me on your fingers. It's not first order. What's the highest derivative I've got? Right, it's order 2. Yeah, second order for sure. Right, we've got a first derivative and a second derivative, so this is definitely a second order. Okay, maybe a harder question. Is it linear or is it not linear? I think it's linear, right? Because every y or every derivative of y, we actually don't have y. That's okay. It doesn't have to have y to be linear, but every derivative of y is raised to the first power and only has not weird coefficients. So this would also be linear. Cool. Let's do another example. I've got a couple more examples. I will point out, I feel like this is a good homework assignment. I feel like I think it's thoughtful, especially the last question where they ask you to figure out which ones are separable. I think that's a worthwhile question. I could see that being a test question for sure. Do these fit here? Yeah, they fit here. Let's do this one first. Find all values of k for which y equal to cosine of kt satisfies the differential equation y double prime plus 25y equals 0. And I'm going to ask again, just like I asked before, what is the order of this differential equation? Definitely second. And for a bonus point, is it linear or not? Definitely linear. Okay, so now the thing we just did is the same thing we're going to do here. We're going to try to figure out what k can be by finding all the things that need to go into this second order differential equation and seeing what k needs to be. So I think I see, well, yeah. So I need to find y double prime. So y prime is going to equal, let's see, the derivative of cosine of some stuff is negative sine of the stuff times the derivative of kt is just k. And then we do it again because we need the second derivative. So we're going to find y double prime. Derivative of negative sine of some stuff is negative cosine of that same stuff times the derivative of the stuff again. So we're going to get a k squared. And then we plug everything into this equation and we see what happens. So I'm going to plug these things in and get, let's see, y double prime is negative cosine of, I don't know why I put parentheses around that, I just did, kt times k squared plus 25y is 25 times cosine of kt equal to 0. And in my opinion, most of these types of questions are going to be find the constant k where the whole thing's equal to 0. In these kinds of equations, factoring is usually your best friend. So you definitely want to factor out as much as you can here. I can factor out a cosine of kt. You could go negative, I guess, if you really wanted to, but I would factor out a cosine of kt. And I would really caution against like bringing something over to the other side and solving. It would probably work out just fine here, but it's good to be careful. So factoring out the cosine of kt, I'm left with a negative k squared plus 25. Which I would probably have chosen to write as 25 minus k squared. And you can either say what the solutions are, or you could factor even further, right? You could write this as cosine of kt times 25 minus k squared equal to 0, which then factors as cosine of kt times 5 minus k times 5 plus k equal to 0. So there's actually two valid solutions here. Our solutions are going to be k equal to 5 and k equal to negative 5. Don't forget about the plus or minus square root thing there, right? We definitely get two solutions here. That's a good question. Well, so that's actually a really good question. And so we'd have to be able to pick a value for k so that cosine of k times whatever t was always 0. And I don't think that works. So I would say, I would actually mention, if it was sine, you could. Because if it was, and actually I think that might, so that kind of question you just asked could potentially come up in question 3 of your homework assignment. Because if this, right, if it were sine of kt instead here, then k being 0 means sine of 0 times t is sine of 0, which is always 0. So I would point out that, yeah, if this was sine instead of cosine, it could be that 0 would always be, with k equals 0 would be a solution as well. Interesting. Yeah. Yeah, I guess that makes sense, right? Because here, so let's just point out, right? If k were 0, just to point out, cosine of 0 is 1. And y equal to 1 is not a solution because the second derivative of 1 is 0, and 0 plus 25 is not 0. But I should also mention, because I think it's a good point, that if we were doing y equal to sine, oh, thank you, appreciate it. We were doing y equal to sine of kt instead, which is also a solution to this differential equation. I believe your values of k would be plus or minus 5 and 0. Because if k equals 0, sine of 0 is 0, and y equal to 0 is definitely a solution to this differential equation. 25 times 0 plus the second derivative of 0 is still 0. 0 plus 0 is 0. So yeah, I'm curious when you do this homework assignment, when you do question 3, I'm curious if 0 will be an answer or not. I feel like it should be, but I don't actually know. So for question 3, my equation is y double prime plus 7y equals 0 on the homework assignment I printed out. So my solutions would be potentially plus or minus root 7 and maybe 0. I feel like it should be, but I don't actually know. I can't see a good reason for it not to be, is what I'm actually saying. But, okay, well then I think you're good to go. That is the third problem though. Let's look at another example. Sure. Yeah. Let me make sure this stuff in order here. No.
Are there any word problems on that one?
On this one here? Oh, on the homework here? No. No, not at all. I mean, when you say word problem, I assume you mean like the kind of problem where you have to interpret the whole thing, and yeah, no, none of that. I'm sorry. It's not, I mean, I suppose. Okay, all right. Well, I'll look for that. Cool. Yeah. All right, let's look at this next one here. One more of these, and then we'll move along to something a little different. Find all values of k for which y equals e to the kt solves this differential equation. So really, again, this kind of problem, same idea. You're finding all the derivatives that you need, plugging it in, and then seeing if you can find the solution. Now, I think this one's a little bit harder. I don't actually know because I haven't done it. Well, let's see. So you guys can work on it too. Y prime is going to be k e to the kt. Y double prime is going to be k squared e to the kt. So I start plugging that stuff in. I've got 9k squared e to the kt minus 12k e to the kt plus 4 e to the kt. And what can I factor out? Right. So here's what happens with specifically with differential equations like this, where it's like something y double prime plus something y prime plus something y equal to 0. It ends up just being like factoring a regular quadratic. If your solution looks like e to the kt, which it usually does. So if we look at this here, if I factor out the e to the kt, I'm left trying to solve 9k squared minus 12k plus 4 equal to 0. And you could either appeal to the quadratic formula, which is not my favorite, or try to factor this thing. I would probably try to factor this thing. Maybe. I don't really want to factor it either, though. So it factors, I'm pretty sure. I think it actually factors kind of. Oh yeah, I think it factors like this. Not quite. So here's the thing. You got 36, right? That's how you. The thing is, the -6. Well, actually, I'm not actually. I assumed you were saying one thing, but I don't actually know what you're saying. So here's what you can do with that -6 if you want to do it that way. You can write it as 9k squared minus 6k minus 6k plus 4. And then factor by grouping. Is that what you were saying, Caroline? It's okay if it wasn't. So what I imagine you were actually saying was it was going to factor like k minus 6 times k minus 6. And it definitely doesn't, because the thing is, if you have k minus 6 times k minus 6, those minus 6's multiply to 36, but we need them to multiply to 4. So the 36 is the right thing to look for, but then you have to do a different thing. You have to see what multiplies to 36 and adds up to -12. And you're definitely right, it's -6 and -6. But then with those -6's, you break that -12 into -6 plus -6. And then we can factor this by grouping. So from that first two things, I can factor out a 3k. I'm left with a 3k minus 2. From the second two things, I can factor out a -2. I'm left with a 3k minus 2. And then from each of these, I can factor out a 3k minus 2. I'm actually left with 3k minus 2 times 3k minus 2, which happens to give me e to the kt times 3k minus 2 squared. So the only solution here is k equal to positive 2/3. Usually, if you were solving something like this, you would get two different values for k, but occasionally you just get one. Or if you don't like this factoring by grouping, we totally could have just used the quadratic formula, right? It's not my favorite, but if we use the quadratic formula, we could have said k equals, let's see, -b plus or minus the square root of b squared is 144 minus 4 times 9 times 4 all over 2 times 9. And notably, 4 times 9 times 4 is 36 times 4, which is 72 times 2, which is 144. So this 144 minus 144, that's just going to be 0. So we end up getting just 12 plus or minus 0 over 18, which is exactly 2/3. But that can be challenging to calculate. So I usually try to go with factoring if I can see how to factor, but sometimes quadratic formula always works. So you can do that. Let's see. I had something else. Where'd you go? What time is it? 10:30. I thought I had something else. Oh, I know what it was. So Caroline, you had mentioned you had a question about a specific homework question. Did we kind of address it, or was there one that you want us to look at still? Oh, okay, I thought you did. All right, that's fine. Yeah. Yeah, I feel like the homework doesn't seem too awful. Yeah, okay.
I think it's just.
I don't feel like this is this is more just like, yeah, that's how I feel too. Like, because I couldn't imagine your test would be only questions like this, because these are all of a very specific variety. I would imagine your test is going to have solving some differential equations, solving a first order linear differential equation. Oh, I haven't. Should we look at it? Let's look at the practice exam.
He was like, these should be pretty comfortable, except for, you know, like the topic 7 stuff.
Sure, yeah.
But it was like, do 1 through so-and-so odd, whatever, and this, on this page of the book. I didn't see it, but he was saying that it's a different edition
Sure.
than what we have for a see that.
Well, you might be able to, if you look at Kuba's webpage, he has the older edition of the book, and he has the pages, like a PDF file of the page already there to look at. So that might be a way to do it. I also have an older version of the book which I could post pages if you needed it, if you wanted to do that. But let's see, I'm going to the wrong place here. 16C, barn. All right. I'm guessing this would be, where do you think we would find this here? Under files?
Yeah, files.
File exams,
Like,
study guides.
no, it's like spring quarter 2018 exam 1 or something like that. So it's like all abbreviated.
It's in files. Let's see here.
It's old material.
Oh my God, can I use my mouse at all? Maybe. Oh, there we go. Old materials.
Those two at the bottom, yeah. Bottom.
It gives you the key, not just like the blank exam.
Yeah, there's no blank.
Ah, it's annoying.
Stupid.
Yeah, well, I can write problems without you seeing the answer. So let's look at that. Gosh, okay. All right, let's take a look here. Okay, so well, fine, maybe I can do this. Huh? There, okay, so I can't see the other half of it then. So the first couple questions here are very much consider the following differential equations and indicate the order and indicate whether they're linear or non-linear. So for these first 5, right, A through B here, you can kind of see all of it maybe. Let's see. Can we see this? You can see it all right. Kind of. I can write stuff down. It's fine. It's kind of done.
He basically said those are definitely gonna be on there because it's really
Sure.
hard for the TAs to grade.
Right, and they should be easy. So I feel like order should never be a question, right? Order, you're just looking for the highest derivative. Doesn't matter if it's raised to some weird power or not. Ooh, I like this last one's tricky here. So let's look at a couple of examples that I'm going to make up that are similar to this. So for example, here's a boring example: 2y triple prime plus 5y equal to e to the x squared. Order in the court. Yeah, has order 3. Okay, here's one that I think is a little trickier. let's say we had y fourth squared. By the way, just so in case you weren't sure, that superscript with a parentheses around the number, that means you're just doing that many derivatives. And we usually use it after we get to the fourth derivative or at the fourth derivative. Plus, I like this. All right, what order is this? It is fifth, because that squaring the fourth derivative doesn't change the derivative you've taken. So a square or a cube or whatever of a derivative doesn't change its order at all. This is still a fourth order term. This is still a fifth order term. So this has fifth order. Now here, this last one he has in here, I think is tricky. I'm gonna write it as is. The derivative of y times y prime is plus y is equal to 4. I feel like this one is meant to make you really kind of think about it. So it's not first order. This one is definitely which order? It's second order. Because if you took the derivative of y times y prime, you would end up getting a y double prime. So this is second order, but it's a little tricky. Well, so really the thing is the ddx says you're taking the derivative of this stuff here. Right, so you could write this as y times y prime plus y equal to 4. But to actually take the derivative of this product, we'd have to use the product rule. So if I actually want to write this out fully, not that we have to see the order, but to make it more clear to us, if I actually take this derivative here, it's the derivative of the first thing, which is y prime, times the second thing, which is y prime, plus the first thing, which is y, times the derivative of the second thing, which is y prime prime. That's actually how we would write it out without this thing here. And then it's much easier to see, oh yeah, that's a second order differential equation. It is definitely not linear, for sure. Even before multiplying it out, you can see it wasn't linear by the y times y prime here. Okay, let me ask you one more in this similar way, just because I think it's kind of fun. What if I said, I want to, okay, sure. All right, this is going to be shitty. dx cubed of y double prime plus y squared equal to 5. But you don't actually have to do anything. So if you took the third derivative of this expression here, which is what that says, right? D cubed dx cubed says take the third derivative with respect to x of this function. If you take the third derivative of y times y double prime, what's the most derivative you're going to get? The fifth derivative, right? Because when you take the derivative of this the first time, you're going to get a y triple prime. And then when you take the derivative, whatever you've got after the first derivative, you're going to get a fourth derivative. And then we take the derivative of that again, somewhere in the mix, you're going to get a fifth derivative. So basically, you're just adding the number of derivatives. This is a second derivative. You're taking the third derivative of that, and 2 plus 3 is 5. So this would be fifth order. That feels a little extra to me, but not impossible. So basically, the number of derivatives you're taking, just add that on to whatever that highest derivative of the thing you're taking already is. So I have a second derivative here. I'm taking the third derivative of that. So I'm doing 3 more derivatives, which gets me to the fifth derivative. That's kind of fun. And then he basically says, look at all the same equations and tell me whether they're linear or nonlinear. Interesting. So let me ask you both, linear or nonlinear for this first one? Definitely linear, yeah. How about this next one? I'm sorry, it's a little blurry there. Linear or nonlinear? So close, but not. So so let me ask you, what's making it not linear? The square on the fourth derivative. So this is nonlinear specifically because of this term here. You have one of your derivatives raised to a not one power. And annoyingly, this next one is also nonlinear because you have derivatives multiplied by things that aren't your independent variable, right? This really here, this is the indication that it is nonlinear. And for the same sort of reason, the last one that I just made up is also nonlinear. So whether you're talking about order or talking about linearity, the only thing you should be paying attention to is what's going on with y. Right? You could have all kinds of wacky things happening with your other variable x. That doesn't matter. Sure. Like that. Let's look at these next couple ones to see if I think they are worthwhile. Yeah, these are good. I like this first page on his winter exam. I imagine it's similar to the spring exam. Yeah, I mean, I think they're virtually the same test. They're not exactly the same, but they look pretty similar. This is a good first page, right? I like the first page of the exam because he's asking you thoughtful questions and you actually have to think about them for a minute. So here's a good question. Is the following equation separable? And I'm looking, just so you know, I'm looking at the winter one. So is this equation the derivative of, sorry, not the derivative, xy prime quantity squared plus 2y equal to 1, is this separable? And I don't know. So here's what you want to do to see if something is separable. You want to try to isolate y prime first, if it's not already. So let's see here. I'm going to write this out as, what did you do here? Interesting. I wouldn't have done that, but that's fine. That's fine though. So he first does xy prime squared equal to 1 minus 2y. I might have squared them each out personally, but he does probably the smarter thing and just takes the square root of both sides. Now, when we do that, we do have to have the plus or minus. So xy prime equals plus or minus the square root of 1 minus 2y. And then I would probably do, yeah, I like dividing both sides by x personally. I don't know. It kind of, so I think at this point you can start to see that it's going to be separable. I think, maybe not. I don't know. I would probably write this as y prime or dy dx equal to plus or minus the square root of 1 minus 2y all divided by x. And I think at this point you can see, oh yeah, I can bring all the y's to the left and all the x's to the right. I can multiply both sides by dx and divide both sides by plus or minus square root of 1 minus 2y. So we can rewrite this as 1 over plus or minus square root of 1 minus 2y dy equal to 1 over x dx. So the answer is yes, it is separable. Now, I would imagine on an exam, whether or not you're saying it is or isn't separable, you have to show this kind of work. You have to be able to justify that it is separable by seeing that you can actually get them apart from each other, or by trying to do it and not getting there. So let's look at the other separable, non-separable equation, just because I think it's good to see one where it doesn't work out. All right, assuming it's not working out. Oh no, they both are separable. That's annoying. Sure. So if I was asking a test question, I would certainly write one that was separable and one that wasn't separable. Like I can't imagine writing them both being separable. But I guess you gotta change it up every once in a while, do what the people don't expect. Let's look at this one here. This is from the spring one. Y prime plus 1 times x squared minus y squared equals 1. So once again, to even have a chance at separability, you first have to get y prime by itself. That's a must. So first I'm going to divide both sides by x squared minus y squared. So y prime plus 1 equals 1 over x squared minus y squared. I'm going to add 1. So y prime equals 1 over x squared minus y squared plus 1. Minus 1. Good God. At this point, it's probably a pretty safe bet to say that we can't separate the right-hand side. you might do a little more exploration. If I was gonna really like see for sure I can't do it, I would probably get a common denominator just to make sure. So I'd probably be like, okay, y prime equals 1 over x squared minus y squared minus x squared minus y squared over x squared minus y squared. And then put this together as minus x squared plus y squared, so y squared minus x squared over x squared minus y squared. Yeah, it doesn't look great, right? There's no way this, so typically I think the notation needs to be, so this can't be written as a function of x times a function of y multiplied together. And I think it's enough to stop, right? Like once you get to a place where you can see like there's just no way of pulling them apart from each other, I think you can say like, oh, we can't write this in the way we need to be able to separate it. So this is definitely not separable.